So the next question that we have is a very interesting question. We have a charge Q which is being carried from this point B to this point A. There is a dipole moment P vector which is kept over here. This is horizontal. Now we need to find out the work done by external agent in this process. So let us write work done by external plus work done by electrostatic is equal to delta K, which is 0. Therefore work done by external is equal to negative of work done by electrostatic force. Therefore we need to find out the work done by electrostatic force now. Now we know that electrostatic force is a conservative force, therefore this is equal to minus of delta U. This is equal to U initial minus U final. So if we can find out the initial potential energy of the point charge when it is over here and the final potential energy of the point charge when it is over here at this point A, then we can find out easily the electrostatic work done by the electrostatic force. Therefore let us first find out the initial potential energy. This will be equal to the Q into potential at B. This will be equal to Q into potential at A. Therefore this is equal to Q into VB minus VA. So what we now need to find out is the potential at this point and the potential at this point due to this dipole moment P vector. Now to find out that, so we need to find out the potential at this point A due to this dipole moment P vector and at point B. So let us first find out the potential due to this dipole at any general angle theta at a distance r. So for this point, let this be point x, we need to find out the potential at this point due to this dipole moment vector. So what we can do is that, this is a very important trick which you can utilize in other places also when you need to find out electric field due to a dipole also at a particular angle. Since this is a vector quantity, we can take components of dipole. So the two components of dipole will be P cos theta on this side, this is P cos theta, and P sin theta on this side, this is P sin theta. Draw it clearly here. This was the dipole moment P vector. Its one component was P cos theta on this side and another was P sin theta, which is perpendicular to this vector P sin theta in this direction. Now we know that due to a dipole, the potential at a distance r along the dipole at this point is equal to Kp upon r square, and along the equatorial plane due to this dipole is 0. The potential at this point due to this dipole is 0 and the potential at this point due to this dipole is Kp upon r square. Therefore when we have taken components of this dipole, we forget this dipole and we now find out, this was our horizontal line, and we now find out at an angle theta at a distance r, we had this point x, we need to find out the potential at this point. The potential at this point due to the parent dipole will be equal to the sum of the potentials at this point due to these two components of the dipole. Therefore the potential at this point x due to P cos theta will be K into P cos theta, that is the magnitude of the vector, upon r square, and the potential at this point due to P sin theta will be 0 because this lies on the equatorial plane of P sin theta. Therefore the final potential at this point x comes out to be equal to Kp cos theta upon r square. You should always remember this formula, that the potential due to a dipole at an angle theta at a distance r at this point P is equal to Kp cos theta upon r square when this dipole has a dipole moment of P vector. Therefore over here we can write down the potential at B as Q into, this will be K into P cos of 145 degree. We take the 135 degree because we take the angle from here. Kp into cos of 135 degree is minus 1 upon root 2 upon r square. Both of this is r. This path actually lies on an arc of a circle of radius r upon r square minus Va, that is Kp cos theta, that is cos of 45 degree, that is for point A, 1 upon root 2 upon r square. So we get the work done by electrostatic force to be equal to minus 2 kp upon root 2 r square, that is minus root 2 kp upon r square into q. Therefore, this is the work done by electrostatic force. Therefore, the work done by external agent is equal to negative of work done by electrostatic force, that is equal to root 2 kpq upon r square. So our final answer for the work done by external force comes out to be equal to root 2 kpq upon r square. The important thing which we learned in this question was that for dipoles you can take components of the dipoles into perpendicular directions.